Good afternoon, class. We are looking at Chapter 5, Integrals, Sections 5.1 to 5.3, the Fundamental Theorem of Calculus, FTC. So we're going to cover the Fundamental Theorem of Calculus, and then the next section will be the substitution rule. So, reminding you of the basic integration formulas, the derivative of kx is k, where k is a number, is a constant. Therefore, the reverse process, the integral of k dx must be kx plus c. The derivative of x to the power of n is n x to the power of n minus 1. That's the power rule for differentiation. Therefore, the integral of x to the power of n dx should be 1 over n plus 1, x to the power of n plus 1 plus a constant. Needless to say, n can't be negative 1 because it makes this denominator 0. Now, we looked at the proof by differentiating the right side. Also, here's the reverse process. If you look at differentiation, the two steps are multiply by n, the exponent, and subtract 1 from n, the exponent goes down by the integration, which is the reverse process. So number 1 here, instead of subtracting, we're going to add 1, so it becomes n plus 1. And number 2, instead of multiplication, we're going to divide by n plus 1. And that gives us the same answer. Now, if we look at these functions, for example, e to the power of x, the derivative is itself. Ln x is 1 over x, sine is cosine, the derivative of cosine is minus sine. The reverse process, therefore, the integral of e to the power of x must be e to the power of x, and it is plus a constant. The integral of 1 over x must be ln x and a constant. The integral of cosine must be sine and a constant. And the integral of sine must be negative cosine x plus a constant. The trigonometric functions works in the same manner. If the derivative of tan is secant squared, the integral of secant squared must be tan x and a constant. The derivative of cotangent is negative cosecant squared. So the integral of cosecant squared must be minus cotangent x and a constant. The derivative of secant is secant x tan x. So the integral of secant x tan x dx must be secant x plus a constant. If the derivative of cosecant is minus cosecant cotangent, the integral of cosecant cotangent dx must be negative cosecant x and a constant. Reverse process. Just with what we did with differentiation, if you have a constant, you can take it outside the integral sign and work on it. If you are integrating a bunch of terms, do them term by term. That's the meaning of some difference rules, everybody. And if the derivative of e to the power of kx is itself times k, its integral must be the same thing divided by k. So the integral of e to the power of kx dx is 1 over k e to the power of kx and a constant. So that should be pretty straightforward, everybody. Now, 5.1 to 5.3, the fundamental theorem of calculus, the method of exhaustion. Areas of familiar polygons, such as triangles and rectangles, enable us to find the areas of more complicated regions by filling the region with increasingly smaller elements of known areas. So take a look at what's happening here. You have a three-sided figure, a triangle, a four-sided figure, a square, and so on and so forth. This is called the method of exhaustion. As you can see, the area gets closer and closer to the actual area of what we are interested in this case is a circle. This is before they knew the area was pi r squared. If we want the area under this curve, it works in the same manner because we don't have a geometric shape that we can calculate. So here's the area problem. Find the area of the region S that lies under the curve y equals f of x from A to B, x equals A, x equals B. This means that S is bounded by the graph of a continuous function f, where f of x is larger than or equal to 0. We are looking at a positive function. The vertical lines x equals A and x equals B and the x-axis. In other words, If you look at this region is between two vertical lines, x equals a to b. That means the interval of a to b. And then between the graph of the x-axis, between the line, the x-axis, which has the equation y equal to 0, and y equals f of x. So the synopsis of that we can write S is the set of all points x comma y such that x is between a and b inclusively, y is between 0 and f of x. So how do you find that area? We use the same concept, the method of exhaustion with rectangular strips. So we cut this into so many pieces. So in this case, if we cut it into 4 pieces, then b minus a divided by 4 would be the width. The width is b minus a over n in general. And this is called the Riemann sum. So the summation of f of x of I delta x as I goes from 1 to n. So f of x of 1 times delta x all the way to f of x of n times delta x. In other words, it depends on what you want to pick as the height. The width is fixed. Delta x is b minus a over n. Although it doesn't have to be, but it makes it better when it is. If I look at the end points, the left end points, for example, the height for this rectangle would be this. For this rectangle would be this. For this rectangle would be this. And for this one would be this. So if I pick the left end points, I add those areas. How do I add them? The width times the height. This is f of a. This is f of the next point and so forth. If I want to go with the right end points, the height for the first one is this one, or this one is this one. So this one. So the shaded region. Or I can pick the midpoint. This is the midpoint. This is the midpoint. 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 And we can add those areas. None of them is the area. Each and every one of them is an approximation. So the function f of x is positive on some interval of a to b. Determine the area of the region between the function and the x-axis. A simple example. Determine the area between f of x equals x squared plus 1 and x-axis on 0, 2. In other words, we want to determine the area of the following shaded region. First, I want you to understand that generally speaking, we would be dealing with this function. Remember, y equals x squared, and it's been shifted up by 1. But the reason we want to limit that because we want the area between 0 and 2. So that is the formula. Delta x is b minus a over n. And let's say we are going to use 4 rectangles. We just come up with some number. Normally that number is given to us. So the width is delta x, b minus a over n, in this case 2 minus 0 over 4, which gives us 1/2. So we cut this into 4 rectangular strips. The width is fixed at 1/2 or 0.5. So if I want the right end points as the height, everybody, that means f of 0.5, f of 1, f of 1.5, f of 2, they will be the heights. So, for example, this one is f of 2. That is the height, everybody. The width is fixed at 1/2 or 0.5. So to calculate, we're going to call it R4 YR because we are using the right endpoints. The width is fixed at 1/2. The height, f of 0.5 or 1/2 plus f of 1 and so on. So the first point is here. Remember that this is the first point. This is the last point, everybody. So f of 0.5 or 1/2, this one, f of 1, this one, f of 1.5 or 3/2. So you go to this function. If you plug in 1/2, you get 1/4 and 1, 5/4. If you plug in 1, 1 and 1 is 2. If I plug in 3/2, 9/4 and 1, over 4. If I plug in 2, 4 and 1 is 5. That's how we arrive at this. We add them up to 5.75. Now, if we use the left endpoints, this would be the height for the first one, second one, third one, fourth one. And for example, the first one, this much is the height. So it looks like that. So now we call it L sub 4 or left. So we use f of 0, f of 0.5, f of 1, f of 1.5 for the height. The width fixed at 1/2 or 0.5. So notice these two are the same. For the right endpoints class, we use, if you just look at the bottom from 0 to 2, okay, 0 to 2, we use all of these points except the first one, 0, for this one. Whereas for the left endpoints, we use all of them except 2. So for this one, we don't use the A. For this one, we don't use the B. A is 0, B is 2. So plug in. And the reason I'm showing you these two are the same because if you're calculating by hand, so this part, you don't have to repeat it. So what is the area we don't know, but it's somewhere between these two numbers. Clearly, this underestimates and this overestimates the area. And as I mentioned, one easy way, if you look at this line segment from 0 to 2 class, from 0, A equals 0 to 2, B equals to 2, cut it into whatever n is. Cut it into 4, and the end points are 0, 0.5 or 1/2, 1, 1.5 or 3/2 or 2. Okay. For the left endpoints, use all of them except B. For the right endpoints, use all of them except A for the height for the functional map. Let's repeat the question, but this time use 8 rectangles. So delta x is b minus a, 2 minus 0, over n, which is 8, and that's 1/4 or 0.25. So if we do the drawing, you see that clearly we have a better approximation. We call it R sub 8, R, because it's the right endpoint, sub 8. And if you look at this line segment from 0 to 2, which has been cut into 8 pieces, we use all of those except the first one, 0, except 8. See, 0.25 or 1/4, f of 1/4, f of 2/4 or 0.5. On purpose, I'm putting 2/4, 3/4, and so forth. We know it's 1/2. So you see how we cut them into pieces. We calculate this. We do the same thing for the left endpoints. When we calculate them, again, notice a big chunk are identical. So if you're doing it by hand, for this part, you calculate this and you keep it. For the next part, you just add f of 0. By the way, I'm factoring the 1/4 out. You see this one? We can factor the delta x out. And that is a different number, 4.1875, and the area is somewhere in between. Notice the area when n is 8 is between these two numbers that they have a difference of 1. Going back to 4, remember, is between these two numbers the difference of 2. Clearly, approximation gets better as n gets larger. That's one observation. Approximation gets better as n gets larger. In fact, for the same question, if you go probably with n equals 20, they become extremely close. In fact, in some instances, they just say, continue with this process until the difference between the two is within a decimal or two or so. Both of them, I hope you recognize the graph as increasing and concave up. When the graph is increasing and concave up, the right endpoints overestimate the area. The left endpoints underestimate the area. Okay. That is the case for increasing and concave. So what did we learn? The fundamental theorem of calculus, section 5.1 to 5.3. Suppose a continuous function f is defined on the interval of a to b if the interval is divided into n subintervals so that delta x is b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x all the way to the last one. X sub n is a plus n delta x equals b. Then a Riemann sum associated with f is the following sum, summation of I going from 1 to n of f of x sub I delta x is f of x sub 1 times delta x all the way to f of x sub n times delta x. Add them up. X sub I is any point in the interval of a sub I minus 1 and a sub I. Any point in between will do the job. Now here's the geometry and procedure. Number one, partition the interval of a to b into a few, let's say, 4 subintervals. Make 4 rectangles. The width is fixed as delta x equals b minus a over 4. The heights are f of x sub 1, f of x sub 2, all the way to f of x sub 4. We are using the right endpoints. Then change it to 8 or more. Eventually, as the number of rectangles increase, the approximation gets better. So here's the approximation. A is almost summation of f of x sub I delta x as I goes from 1 to n. In this case, the n was 4. And if you expand, it looks like that. The left endpoints, the right endpoints, and the midpoints. For the left endpoints, f of x sub 0 or a is used, but f of b is not used. For right endpoints, f of x sub n or b is used, but f of x sub 0 or a is not used, and the midpoint is in between. And the best course of action, instead of memorization of this formula, just call this a, call this b, and cut it into however many pieces. For example, if it's 4, pass. For the left endpoints, use all of this except b. Don't use b for the left endpoint. By that, I mean don't use f of b. For the right endpoints, use all of them except a. Don't use f of a here. What about the midpoints? Just use this point as the midpoint, and the next one, and the next one, and the next one. And how do you use it? Figure out the first and then add delta x. So those are approximations. What is the actual area under the curve? The limit as n goes to infinity of summation of I from 1 to n of f of x sub I delta x, where delta x is b minus a over n, and x sub I is a plus I delta x. This is an exact area under the curve. Now, FTC has 2 parts. One of them in the interval of a to b. And of course, f is a continuous function. d dx of the integral of a to x f of t dt is f of x. That means if you take the integral from some number to x and then differentiate it with respect to x, you get the function back. So that means differentiation and integration undo each other. The next one is the integral of a to b f of x dx. This is capital F of b minus capital F of a, where capital F of x is the antiderivative of lowercase f of x. So this is the area under the curve, and it's pretty tedious. It is equal to this one, which makes it a lot easier, as long as the function is positive. If it's not positive, then it represents the difference of areas. Now, so what are we dealing with here? Integration symbol. The symbol was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is the limit of sums, lower and upper limits of integration. Integrand, dx variable of integration, also called a dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. The dx simply indicates that the independent variable is x. Notice, class, this one, the integral of a to b f of x dx, is just a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral. So the integral of a to b f of t dt is also the same. Its approximation, the integral of a to b f of x dx, is the summation of I going from 1 to n f of x of I delta x, which is f of x of 1 times delta x all the way to f of x of n delta x. This is the Riemann sum. This sum is called a Riemann sum. The precise value is when we take the limit. A is precisely equal to the limit as n approaches infinity of summation of I from 1 to n of f of x of I delta x. This can be very tedious, whereas this FTC makes it much easier. For example, if we want to evaluate the integral using the areas, this is the integral of -2 to 5, 3 times dx. You should notice the function y or f of x is equal to 3 is a horizontal line. And we want the area under this curve from -2 to 5. So plot that from -2 to 5. So this is the x-axis, this is the y-axis, this is y equals 3. And we're going to go from -2 to 5. So -2 comma 3, 5 to comma 3. And this definite integral represents the area of a rectangle of width 5, this width, 5 minus minus 2 or 7, and the height of 3. So this rectangle. This is a simple geometry. The product of 7 and 3, 21 is the answer. So this is using geometry. So what happens is we can easily use the geometry here. However, FTC says, well, we can use this method. The difference is if this fails, in other words, this is not a geometric shape, we know the area, how it's calculated, we can follow that. So the antiderivative of 3 is 3x. We want to evaluate it from the lower limit -2 to upper limit 5. So you plug in 5 and then -2, you can take the 3 out. 5 minus -2 equals 21. That's how we evaluated f of b minus f of b. As you can see, they are identical. So what's the difference? Well, not much of a difference here. But if we can't use a geometric shape, then we better stick with FTC. Here's another example. Evaluate the integral using signed areas. So use the signed area interpretation of the definite integral to compute the integral of -2 to 2x dx. So first of all, the function is x. And we are going to go from -1 to 2. y equals x or f of x equals x is a line through the origin. Again, we know the graph. Okay, everybody? That's the assumption. We want to go from -1 to 2. So we want this area minus this area. Why is that? Over here, the function is positive. Over here, the function is negative. So it's the signed areas, the difference between the two areas. And each one is a triangular shape. We follow a equals half of base times the height. Notice this one has coordinates 2, comma 2. So this one and this one, 2 times 2 divided by 2 gives you the area equals 2 for the green part. For the red one, this one has coordinates -1, -1. So this has a distance of 1. This has a distance of 1. Their product is 1, half of it is 1/2. And the signed area says the difference of the two, which means 2 minus 1/2 or 3/2 is the answer. So again, you are looking at a shape where you have a geometric formula for it, half of base times the height. But if we don't have that, and that's the idea, everybody. We use FTC. So x gives us half of x squared. By the way, we don't need a constant because it will cancel out. So you plug in 2, you get 4. You plug in -1, you get 1. 4 minus 1 is 3 times 1/2. So 2 gives you 4, -1 gives you 1. The difference is 3, and the final answer is 3/2. And that's exactly what we have right here. The difference is this will always work. This one, if you don't have a geometric shape that you know the formula for, it won't. So what I want you to do, I want you to graph and use signed areas to show that this integral is -45. So I'm giving you the question, I'm giving you the answer. I want you to verify it 2 ways. One by graphing it, one by FTC, and FTC will always work. In this case, the shape also is, you can follow a geometric shape and come up with the answer. It's really not a big deal, but please do so. It's a good practice. Evaluate the integrals. X to the power of 7 dx is 1/8 x to the power of 8. It's a simple case of a power rule, everybody. Evaluation from 0 to 1. First, you plug in 1, you get 1. 0 gives you 0. 1/8 times that is 1/8. So that's very straightforward, and reminding you that even, this is a tip, even if we use another antiderivative, capital F of x plus c, in other words, 1/8 x to the power of 8 plus a constant. In the evaluation theorem, the result will be the same because capital F of b plus c minus capital F of a plus c, those c's cancel out. So if I put plus c, I plug in 1, I plug in 0, the c's cancel out. That's why we don't waste time. The integral of 1 to 2 x to the power of -1 dx, reminding you that means 1/x, and therefore the answer is a natural log. So ln2 minus ln1. ln1 is 0. The answer is ln2. Again, as always, go with exact answers in calculus. Now I want to look at part C, which is very similar to that. And so the answer is the same thing, natural log, but of course we have different limits. The reason I am going with this question because I want you to see that in part B, if I lose the absolute value, makes no difference. But in part C, I can't because natural log of negative numbers are undefined. Remember, the domain is from 0 to infinity. So this is ln1, which is still 0. And this is ln2, so minus ln2. That's why you want to keep the absolute value sign because it makes a huge difference in part C, not in part B. The integral of 0 to pi sine x dx, and we know that sine gives us negative cosine. And again, we don't need a constant because it makes no difference. Now we want to put pi first and then 0. I'm going to keep the negative sign out. It makes it easier for calculation. So cosine of pi minus cosine of 0. Cosine of pi is negative 1 minus cosine of 0 is positive 1. So they add up to negative 2. The negative outside makes it positive 2. Example 5, part A, the integral of 0 to 2 5x squared minus 4x plus 2. We are going to use the power rule. So 5 divided by, you add 1, becomes 3 5/3 x cubed. This one, the exponent is 1, so it's minus 4 over 1 plus 1, x to the power 1 plus 1. That means minus 2x squared plus 2x from 0 to 2. You plug in 2, you plug in 0, and I hope you recognize if you plug in 0, you get 0. So you plug in 2, 5 halves, 2 cubed is 8, 4 thirds. This is 4 minus 8 plus 4. You get minus 4. 4 is 12 thirds. So 40 thirds minus 12 thirds is 28 thirds as the final answer, everybody.